Hello again, Year 10, and welcome to our last PowerPoint for the summer. So, hopefully you enjoyed, or at least tolerated, the reactions of the alkenes. It's a bit of a bulky topic in terms of things to learn, that one, or subject area, not topic, it's just a subsection, with all of those many different reactions, and some really quite high-level chemistry used. Talk about mechanism stuff. No mechanisms today, you'll be glad to know. We'll only briefly touch on the idea of mechanisms again, and again, you don't really need to know any mechanistic stuff. It's just to try and help you. So, without further ado, what are we doing today? Well, we're looking at alcohols and carboxylic acids. So, we're going to look at the structures of alcohols and carboxylic acids, the properties and uses of alcohols, and we're going to be looking at the properties and uses of carboxylic acids. There's a little bit of sort of how science works discussion at the end. I can't remember if I deleted it. So we will finally go to the root. That's an exciting thought. So, first little task is I've got here two molecules, ethane and ethanol. Slight pause there as I was checking I'd actually written ethane next to it. So what I'd like you to do briefly is pause the PowerPoint and work out as many similarities and differences as you can between the molecules. I have a list, but not the exhaustive list, that I'll share in a moment. So pause and carry on. Okay, so similarities. I came up with they have the same number of carbon atoms. They also have the same number of hydrogen atoms. None of them contain double bonds, so they're both unsaturated, or they only contain single bonds, so they're both, sorry, I said unsaturated. I meant saturated. They contain no double bonds, so they're both saturated. They contain only single bonds, so they're both saturated, and they both begin with the name eth because they both have the same number of carbon atoms too. They are both organic molecules, and by that we mean they're built around a carbon structure. That is fundamentally what organic molecules mean. Hopefully that mic's still working. Okay, so what about their differences? They both have a different named suffix, which corresponds to the fact that they have different, or one of them has a functional group. And one of them has an oxygen atom. Oxygen atom is what defines the presence or absence of a functional group on the ethanol. Not both of them are hydrogen are hydrocarbons, because ethanol is not just made of hydrogen and carbon, it's also made of oxygen. Only one of them has a functional group, so therefore they have different functional groups, or only some functional groups, whatever. There's a difference in the functional groups. And they are both from different homologous series. So there are two words there that are significant, really significant. They are functional group and homologous series. So let's have a look at the details of what those two mean. And by the way, if you've come up with any other differences or similarities, do feel free to let me know, because, like I say, it's not an exhaustive list, but it's kind of all the important ones that I could think of. Okay, so what is a functional group? So before we get to that, all organic molecules are built on a hydrocarbon skeleton. So they've all got this chain of carbons with hydrogens often. Now you can do all kinds of fun things with that, make this chains branch or do all kinds of weird things, but fundamentally all the organic molecules are built on that carbon chain with hydrogen stuck around the edge. However, you can drastically change the chemical properties of these organic molecules by adding different things onto that hydrocarbon skeleton. And these different things you can add are called functional groups, because they do specific chemistry. So, we can put these functional groups on, and functional groups are a specific group of atoms on an organic molecule that are responsible for its chemical properties. There are better definitions of functional group than that, but they tend to be a bit more wordy. As far as I'm concerned, that will do fine, because it's a bit of the molecule that defines its chemical properties, or can define its chemical properties. It is entirely possible to have multiple functional groups on a molecule, and only some of them be the ones that are the most significant. Now we also have to mention the word homologous series, which is a really unpleasant sounding word, but isn't too bad. It basically just means family, or family of specific types of organic molecule. So far we've met two homologous series, the alkanes who are as boring as they get, and the alkenes, who with their double bonds are rather more chemically interesting. We're going to add two more series today, the alcohols and the carboxylic acids. Annoyingly, carboxylic acids don't begin with an alk, but never mind. So, a homologous series is a family of organic molecules that contain the same functional group, either there may be plural there, but have a different length hydrocarbon chain. So far we've just learned the functional group for the alkenes, that double bond. And that is what makes an alkene an alkene. It defines it, and it defines all of its chemistry as well, because the only chemistry that doesn't get defined by that is its combustion reaction. And most alkenes, and a lot of other organic chemicals will still undergo combustion in the same way as any other, because they've got that hydrocarbon chain, and it's that which is controlling the chemistry of combustion rather than the functional group. The functional group does the more interesting chemistry, but is not just straight off burn. Okay, so there's our one functional group so far. However, we have two new ones, like I said. The two new ones are the alcohols. That's the OH functional group. Now you might have noticed on my earlier ethanol, I did not draw a bond between the O and the H. That was simply because I was using an old picture. At GCSE, you are expected to draw this bond in. I have no idea why, because nobody else in the world does it. That OH bond, of course it exists, but any other bit of chemistry that you'll ever do in your life, other than GCSE chemistry, will just selectively forget the OH bond, because it's inconvenient to draw, it's a pain in the neck, we know it's there, it's also not specifically always behaving like a covalent bond, and a whole load of other reasons it means that nobody else ever draws that OH bond. A level you don't draw it, degree level you don't draw it, if you're a professional chemist you'll not draw that OH bond, whatever. That's only here, only drawn at GCSE. I don't know why. Anyhow, so these are the alcohol homologous series. And then there is this weird looking beast over here. Now this is an acid group. So here we've got the boring hydrocarbon chain, just one carbon currently, and the last carbon, the second carbon in this molecule, forms a double bond to one oxygen, and a single bond to an oxygen and a hydrogen. Again, I should have drawn a bond in there, but these I've taken from the internet. It's actually quite hard to find pictures of the acids with that single bond between the oxygen and the hydrogen. Again, because like I say, nobody actually draws it except GCSE scientists. So apologies that you guys get the slightly rough end of the deal there. So the COOH group, this whole chunk on the end here. Oh, that was a bit of a weird circle, let's try that again. The COOH group on the end there, that defines the chemistry for the carboxylic acids, just like the OH group here, the hydroxyl group, determines the reactions of the alcohols beyond burning. That's called the acid one's called the carboxyl group, in case you care. Moving on. Okay, so let's start off looking at the alcohols. First up, what do we need to know about them? Well, let's do the naming. So the names, I have a cat jumping off my keyboard, so hopefully you won't press anything. Names start like any other organic molecule with the main root, and that is just to count the number of carbons in the longest chain of carbons. Again, you will not be faced with anything that have multiple lengths of carbon chain or branching chain, so it's just basically count the carbons. Or at least all the ones that are connected directly to other ones, because you do have to do the one ester. Again, not until after the summer though. So, the first one is monkeys, it's neath. The second one is eat, it's heath. The third one is prope, for peanut. And then we've got butter for butte, and then of course pent, because of the inconvenient way the specifications are written. Now how do we name them? Well, the second bit is we have the suffix. Now alcohols have a suffix of ol. But we also include a little bridging, I'll call it a little bridging fragmented word, which links the F to the ol and tells us it's saturated. So it doesn't have a double bond. If it was unsaturated, it would be enol, or en, but you don't actually know that. So it's F-an-ol, and the an is just there to tell it's saturated. It's effectively a way of saying nothing else to see here. Just draw an alkane and stick an OH on the end. Okay, so there's methanol, and ethanol, and propanol. Now, the alcohol group can be drawn anywhere on this molecule. It doesn't have to go at the end of the chain. It's perfectly capable to replace any of the hydrogens on the molecule, and in real chemistry you don't have to describe where it is using what's called a locant. We stick a random number into the name, like propan-1-ol is what's drawn there, but you could equally put it in the middle carbon and call it propan-2-ol. It doesn't matter. At GCSE we don't care. It's just propanol. All the possible propanols are called propanol, and we don't even know locality stuff, so we'll just always draw it from number 1 position on the end of the chain, because that's kind of easier to remember. Okay, so the general formula. Just like the alkanes, which was CnH2n plus 2, and the alkenes, which was CnH2n, we have to be able to recall a general formula for the alcohols so that you can work out any you need to in any exam question. So let's have a look at how this works. First off, actually, I've got the same number of hydrogens as I would have in an alkane, and that's true of all of them. The only difference is I've got an extra O, so I could, all I've done is I've changed an H into an OH, which is just adding an O. So I could just write CnH2n plus 2 O, and that's fine, and you could do that, and you'll get the mark from GCSE for it, because GCSEs don't really care about structure when you write formula. But that doesn't clearly show the hydroxyl group, the OH group. So actually, if you're doing it as a proper chemist, we'd use CnH2n plus 1 OH. And that way, right at the end of the molecule formula, you've got the OH clearly showing that it's an alcohol. And it makes it obvious for you when you've drawn it as an alcohol, and it just, looks a bit nicer. But like I say, this version, actually that's perfectly valid. If you wrote that for the general formula, or a formula you worked out using that in a GCSE, you should get all of the marks, no problem at all. Next. Okay, so I've got a little task for you here, and it is fundamentally the same as the previous ones. I've got the number of carbon atoms, the name, the formula, the display, relative mass. I think I haven't changed alcohols on the acid one, so I'm going to scribble that out unknowingly when we get to it, but that's okay. So I've done a couple of relative masses. I've given you one display formula. You just saw the other 3 there, so if you're really carbon on this, scroll back in time. You can probably work out the molecular formula from the display formulas, and that just leaves, I was about to say its name, this one, the bute and something or other ol. Obviously it's not called butan something other ol, that's just me being silly. Where you can work out the whole thing, but that shouldn't be too bad. I think I checked these, so they should be right. If they're not, tell me. I'll apologise. So pause, spend some time doing that. I don't have the answers on this PowerPoint because I'm going to mark this as your assessee thingy to do, because I'm not supposed to give you too many of those. So mark those, so do those. There aren't many exam questions I can set on this yet, because they tend to be all diagnostic and throw the whole topic in together. We haven't finished it yet. So fill that in and carry on when you're ready. Okay, properties and uses of alcohols. So I wasn't really going to do this in this lesson, but I have done, so we'll probably do it again after the summer to see if we've remembered it. And this is how they behave and what they're useful for. So first of all, they are extremely common in everyday products, particularly ethanol. I mean, let's be honest here, most of you aren't going to know ethanol because you drink it, hopefully. You're going to know ethanol because you've been cleaning your hands with it for months and months. There's actually quite a lot of the alcohol gels aren't made with isopropyl alcohol or isobutyl alcohol or one of the other alcohols. Quite a lot of them are actually made with ethanol, which is perfectly fine and good at killing things because it's fairly reactive and, well, a poison, fundamentally. They are pretty soluble in water because of that OH group. They behave very much like the OH group on water. They dissolve in water pretty well until they start getting really big. And this also makes them useful as solvents. When they dissolve, they're neutral solutions, so they don't behave as acids or alkalis in these circumstances when just dissolved in water. As I said, they're very useful solvents, and this means that you'll end up with them in paint sometimes, or paint thinners, nail varnish removers, things like that, where you need to dissolve things, or meths, if you manage to spill ink on something, methylated spirits, white spirits will remove it quite nicely. The main difference is an interesting fact. At university, we used to have bench ethanol until the university became wise to the fact that students, not myself, were stealing bench ethanol, putting it in mixers and having very, very, very cheap drinks with serious power. And so they started replacing our nice bench ethanol, which is expensive because you've got to pay alcohol tax on it because it's alcohol, with ethanol that had the label, it's now called IDA, but ethanol brackets containing methanol a deadly toxin? Because, well, most students don't drink things that are definitely going to kill them eventually. At least not as often. Okay, here we go. Solvents, aftershaves, mouthwashes, good uses of alcohols. Now, the chemical reactions of alcohols we will come back to, but once again, they burn cleanly. Presence of oxygen makes them burn in general more cleanly than others. They're also fairly volatile. Ethanol, well, it's less volatile than, say, ethane, but it's still pretty volatile, burns, and then burns nicely. The diagnostic test for ethanol is if you put sodium into it, it will sink to the bottom, showing it's less dense, showing that its density is different to that of water, and will fizz, producing hydrogen gas and dissolving the sodium. Now this is specifically ethanol at A level, but as far as you're concerned, it's alcohols generally. But yeah, we'll call it ethanol. That doesn't matter too much. You won't get asked about it except for that one. We can also oxidize ethanol. This is one of the key reactions. If you add oxygen to ethanol, you can actually turn it into a carboxylic acid. There's a sort of halfway house, a couple of chemicals that are a halfway house that you don't need to know anything about, called aldehydes and ketones. But we actually only care about the oxidizing to an alcohol at GCSE. And essentially, you just add more oxygen until the OH group becomes an O double bond and an OH group, and strips a load of hydrogen off. And that is as oxidized, apart from burning, as you can make an alcohol become, and that's called a carboxylic acid. And so you can do that by adding an oxidizing agent that is not as good as just oxygen to a solution and what we call refluxing it. And that reflux just continues the reaction until it's definitely all oxidized. Examples of oxidizing agents are potassium dichromate or acidified potassium dichromate solution. And that's pretty much the one you might be asked about or might need to know. But really you can get away with just saying oxidizing agent. That is plenty. So oxidizing agent is the key thing we need to say to turn an alcohol into a carboxylic acid. And you'll know this because you've probably all encountered vinegar in your life, and you've probably noticed that some vinegars are labelled malt vinegar, and some are labelled white wine vinegar, and presumably there's a red wine vinegar that would be very nice. And that's exactly where they come from. You just basically open a bottle of alcohol and leave it in the air, and the air will slowly react with the alcohol. The oxygen in the air will react with the alcohol to produce the carboxylic acids. So if you leave wine open too long, you get a distinctly bitter tasting wine because it's full of vinegar, very literally. So that exposure to air, the presence of microbes, produce the oxidation of the alcohols to make the carboxylic acids, which, you know, taste strongly of bitter vinegar. There we go, that's the part that animates up as well. Cool. Right, so our next homologous series are the carboxylic acids. So down the left-hand side, I've drawn the first three, or to be honest, I've stolen from the internet the first three, and that explains why the top two do not have a bond between the oxygen and the hydrogen, because, you know, the internet is a place where people tend to include the real chemistry, not the GCSE chemistry, and it's actually surprisingly hard to find a no background methanoic acid or ethanoic acid where there is a bond shown between the oxygen and the hydrogen, because nobody does it, apart from the GCSE students. So there you are. I'll put a bond in there, and I'll try and stop moaning about this. I promise nothing, but I'll try. So, let's do the naming again. This time it's exactly the same as all previous attempts. They've all got the generic molecules, with the main root, which comes from the length of the hydrocarbon chain, so meth, eth, prop, bute, and pent, which of course don't appear on my PowerPoint. And then again we have to add the suffix, which is the name bit at the end that makes them different. So in this case the suffix is oic acid, and just like the alcohols we stick an an in there, A to make it sound nice, and B to tell us that it's a saturated hydrocarbon, and I did say it correctly this time, which is a bonus. So oic acid becomes anoic acid, and therefore it's meth-anoic acid, eth-anoic acid, or ethanoic acid, and propanoic acid. So those are our first three. Of course, bute would be butanoic acid, and pent would be pentanoic acid. There are, if you search the internet for the names of this particular homologous series, you'll find that there's a bit of a confusion that used to exist. The old systematic naming of these things, well, okay, first of all, We didn't always used to name stuff systematically in chemistry. We used to just give it names, depending on how similar it was to other stuff, because the structures weren't well understood. And then we started to give them sort of slightly systematic names. And then eventually someone figured out that actually, you know, we ought to do all of these properly, and we created what's called IUPAC, which is the International Convention for Naming Stuff Properly, not in those words. So the IUPAC nomenclature is now that the number of carbons in total give the meth-eth pro bit. But historically, you didn't used to count the COOH bit as part of that chain. So methanoic acid, old-fashioned methanoic acid, looks like new-fashioned ethanoic acid, which is just massively confusing for everybody. So this is the correct ethanoic acid, this is the correct methanoic acid, and this is the correct propanoic acid for up-to-date IUPAC science. And anything that doesn't say that is too old to us to care about. You also have absolutely no need to know names like glacial ethanoic, which is the old name for ethanoic acid, and things like that. Just seriously, those 3 or those 5 is plenty. Don't try and look at the old names because they're a pain in the neck. I haven't bothered learning the old ones, which always makes me feel a little bit out of touch when I'm talking to older chemists because they're like, organic names made up. I'm like, systematic, please use the proper ones because I actually know what you're talking about then. Okay, the acid group can only be drawn on one end. It always occupies position 1 because look, it's got to have 3 bonds for the acid. If you stick it in the middle of the chain, you've just broken the chain because that carbon can't form any other bonds. So this functional group has to be on the end of a hydrocarbon chain, and therefore it's always on the end of a hydrocarbon chain. So in fact, it's one of the rules of naming stuff when you do naming stuff properly that it's always in position 1, because it's the thing that's most overridingly, not important, but most overridingly in the suffix, for what we call priority, which I don't care about. Okay, so general formula of acids. This is a slightly more contentious one, and again I'll explain why. So the alkane, they have formulas that basically the same as the alkanes, but you take away 3 H's from the end and replace them with the OOH. Now you could therefore write the formula as CnH2nO2, and that would absolutely get you the marks in the GCSE, but it doesn't show you the presence of the OOH group, and I mean COOH group. So the one I've created is a little bit fiddly, but it'll get you a formula that actually kind of shows that it's carboxylic acid. And the formulas that we generate as a result is what I want to see. So this is the confusing bit. I've written Cn-1, and that's because I've got a C over here. So basically, you need to know how many C's there are in total, and write all but one of them here, and then the last one there. And then H, 2n-1, COOH. So 2n-1, so okay, let's try that. Formula for, let's go with ethanoic acid. Cn-1, well I've got 2 C's, and C2-1 is C. H2n, well I have 2 C's, so that's 4, minus 1 is 3. CH3, done, COOH. My O's are on point today. My mouse must have found a bit of a mouse mount that doesn't have a silly blank bit of colour on it. So CH3, COOH. Let's just check that. CHHH, COOH. Done. Perfect. So my ability to make up random formulae appears to work fine. Just be aware that it's a bit silly. Feel free to learn it, but learn it with intelligence. If you can't handle that one, do by all means use this one. It just won't give you the structure. It doesn't give you that COOH group on the end, so it's not always as obvious what it is you're dealing with. But again, your GCSE mark schemes generally do not care as to whether or not you're showing the existence of alcohol or carboxylic acid. They tend to want you to just see the right number of carbons, hydrogens and oxygens. I just tend to like having a little bit more data because the next question might be asking you what that thing is or what that thing does. And being able to see the acid, the alcohol group might give you a little advantage there. Moving on. Oh, this is the bit I got. Yeah, look, alcohols. That's annoying. Acids. I'm not going to write carboxylic acids. I should, but I think... Oh, let's give it a go. How bad can it be? Oh, you know what? I didn't cross out saturated hydrocarbons either, did I? I just put in alcohols and didn't even remove that. So that saturated, unsaturated box up there is nonsense. Well, The saturated's fine, the hydrocarbons is nonsense. Carboxylic acid. It's a word that I always worry about spelling carboxylic. But somehow I don't spell that wrong, whereas I do regularly spell gas wrong. Who knows? Carboxylic acids. Okay, once again, it's the usual drill. Here is a table. I've told you all the names several times. We've discussed the general formulae. I've put them in the form that I want to see them in, which is the one which shows the COOH. That's only because I'm a chemist and I love chemistry, so I kind of want to see them in as much chemistry as possible. If you want to do just how many carbons, how many oxygens, how many hydrogens, how many oxygens, I suppose I'll survive. Display formulae, no negotiating, you have to draw it like that. Please show that single bond there, even though I don't. That single bond does need to exist for reasons. And then relative mass calculations. I only messed one of these up because I tried to do hexanoic acid rather than pentanoic acid. And then looked at it and went, yeah, that's wrong. Ooh, I've got an email. How exciting. Right, get those filled in, please. Pause, take it on as you like, and then carry on when you're ready. Okay, so carboxylic acids, what are these beasties like? Well, first of all, they're acids. They all dissolve in water to make acidic solutions, pHs of less than 7. And that is definitionally what acids do. What else can they do? Well, animation of the picture. They behave exactly like any other acid, with the caveat that they are weak acids. Not like hydrochloric, sulfuric, and nitric, which are the 3 strong acids you need to know. They are weak acids, and when you did acids and bases, you probably learned ethanoic acid as an example of a weak acid, which is good because it's a weak acid. So are all the other organic acids, the carboxylic acids. And they're all weak acids because they are not quite so good at giving up that H space strong acid. The remaining part of the molecule, the conjugate base, is generally less charged. Okay, or that's not really a very good description at all, so ignore that. This is because strong acids completely out. So definitionally, they are weak acids because when you put them in water, they do not fully ionize. The bond between the O and the H is slightly stronger than, say, the bond between the H and the CO in the hydrochloric acid, and so it doesn't all break. It forms an equilibrium. Equilibrium, which you don't really worry about. But it means that only a percentage of the carboxylic acids release their hydrogen ions, not all of them. And you end up with a significantly higher pH than you would have done for the same concentration of a standard strong acid. Oh, there we go. That's what that says. Useful. Right. Last features we need to talk about, really. We haven't done the reactions of the alcohols and the acids together, because that's next lesson, which is after the summer. And that is esters. And esters are awesome, and there's a practical one. I'd like to do that as a practical thing if possible. So let's hope that public going doesn't cause us to have a massive second spike and we have to go back to school in September, because that'd be useful. Right, organic issues. These are kind of miscellaneous extra things, and there's a bit of extra content I would like to include as well. So, things that I'll find here as organic issues, but don't think it means organic farming or organic chemistry. I think it's just a catch-all phrase. I have mostly written this PowerPoint from scratch today, but I have just kept in a few bits like this one from the old version, which I didn't entirely hate. So, you know from biology that alcohol is bad for you, causes blood pressure, heart disease, and liver cirrhosis. It's also an addictive drug, so on the whole, people think it's not really necessarily a good thing to use to drink. Historically, of course, it's the cause of civilization coming to exist, because back in the time when you are storing your grain in a granary and you are trying to live together in groups for the first time, so the first villages and towns are springing up, you haven't invented sewers yet, and so what you're doing is you're digging a hole in the ground next to your house, and you're pouring a wee into that hole, and then you're digging another hole and extracting water and drinking it. Those two things are not a good combination because soil is permeable. So if you start putting more than about 5 people in a small area and then living together, and you are drinking water out of a well next to the place where you're going to the toilet, you all keep dying of dysentery, etc. So you cannot have towns or cities until you've developed drinks that are not going to kill you. And the key drink that you develop is alcohol, because tea requires energy input, and the plant tea, which is non-native to most of the places where humans were doing early evolutionary things like learning not to live independently individually. So some cultures have tea as a higher influence, but the West, quite a lot of other places, developed their cities based on beer, small beer. Everyone would drink small beer all the time because it had just enough alcohol to kill most of the bacteria that would otherwise cause you to have dysentery all the time and die. And I say dysentery, and dysentery is actually caused by a parasite, but alcohol has a very similar effect on those two. So this small beer, sort of less than 1% per volume beer, is what everyone would drink all the time at any age group, unless you were actually drinking milk. And you could basically milk or warm beer, small beer, and it was just alcohol enough to keep it fairly well safe from nasty microorganisms. And so that's how civilization happened, or at least the town and city bit of it. Because, yeah, anyway, that's kind of long, and sorry I got a bit carried away there. Yeah, health problems, antisocial behaviour. You get drunk, you behave like a person, a silly person, that would be. Ethanol can be used as a biofuel, so we burn this stuff. It's great fuel, burns very cleanly, it's very nice, and you can make it out of plants. You don't have to rely on prehistoric deposits of coal and oil to make this fuel. You can just grow a field full of plants. Of course, the downside to that is you're not eating the plants that you didn't grow in the field, you're burning them, and therefore, in a world where, despite having massive excesses of food, billions of people are still starving or living below the breadline, it seems somehow a little bit wrong to be chopping down forests that we're desperately in need of as well to combat climate change, growing plants to burn them for fuel. Except, of course, at least that means we're not adding any more carbon dioxide because it's a carbon neutral process. So yes, there's pros and cons and all the usual balancing act with this kind of process of technology. Biofuels are fundamentally pretty good. Ethanol is a pretty good biofuel because you can just stick it into petrol. That's why your 95% octane thing, or 98% octane thing on petrol pumps, is basically saying not what percentage of this petrol is petrol, but what percentage of this petrol is not petrol, and the not petrol bit is ethanol. So my octane 95 petrol that I put in both our cars is 5% bioethanol, which is great because I'm only burning 95% non-renewable oil-based property, and 5% of it's actually coming from plants, which is kind of the wrong way around. I'd rather it was 95% renewable, but hey, or 100%. The last thing I was going to mention before I can't remember this slide ends the PowerPoint is how we make ethanol. The old spec used to have a lot of detail on this, the new one not so much, but fundamentally it's down to two different processes. A batch process, low-tech production of ethanol, which is what you do if you are making ethanol to drink generally, or if you are a very low-tech country with lots of labour, because you can just plant a load of crops, doesn't really matter what type, harvest the crop, stick it in a large vat, put a bit of yeast in, warm it slightly, and leave it for a while. It will ferment, and then you get a relatively low alcohol mixture, because of course it's a self-limiting reaction. As soon as there gets too much alcohol, it kills all the yeast, and then you can't carry on making more alcohol. So that's going to be anoxic. You have no oxygen in there, otherwise you end up with like proper respiration happening, not fermentation. And then you've got a mixture of potentially tasty alcoholic drink and bits and pieces of leftover material and water. And the other way of making alcohol is take a fraction from crude oil that's all the same size, crack it and distill it to get, say, the one alkene you want, let's say ethene, and then use the addition reactions we saw last week to make ethanol by hydrolyzing it, adding water to it in the form of steam. And that will, of course, make perfectly pure ethanol. So that way of making it is high-tech, low labour-intensive, rapid, continuous process that is not from a renewable source, whereas the alternative is low-tech, high labour intensity, from a renewable source, but the product is a mixture and it's a batch process that takes ages and isn't so clean isn't so pure at the end. Right, I think I've droned on enough for one day. I think when I press the next arrow on this PowerPoint it's going to end. I can't remember whether there's a slide up, this one you see. You've got two summary sheets of the molecules to fill in. If I'm feeling particularly creative next week, I will set you some additional work, potentially feedback based on the work you submitted this week, or are submitting right now as I'm recording this on Monday. And yeah, I would like you to have a really brilliant summer. I would like you to do a little bit of chemistry. Can I recommend the following websites? chemguide.co.uk and Doc Brown's. Both cover multiple exam boards, so make sure you're looking at the AQA chemistry. Any revision you can do on previous chemistry you learned in year 9 and 10 would be fantastic. any extra work you can do on the stuff that we have covered so far, the organic section, would be amazing. And really the thing I most want you to do is relax. Don't forget all your chemistry, but don't do anything to actively increase it unless you particularly want to. Just make sure you don't reduce it by losing it all. And if at all possible, can you come in to September with a list of all the stuff that you think you don't know from year 9 and 10 that you think you ought to know because you've looked at the list of all things you should know and you don't know all of it. So I've talked to a few people, and the few people are quite a lot of you, let's be honest, the IRD meetings did take most of the class. And most of you said moles, and a few of you said structure and bonding. And a few of you said some other specific things like titration reactions, which is a bit of moles that sort of get sneaked into the acids and base topic, and still is also moles, and things like that. So yes, I will happily do those. Please, please, please let me know what you don't like so I can do it. Right, have a wonderful summer. Let's see if the next click ends the PowerPoint. No, it doesn't. Look at that. There's some key points. Here we go. Organic molecules into homologous series, which are families, and those families are defined by the functional groups. Their properties and uses vary, and we can use alcohol in food and drinks and solvents, and acids. Oh, and there are some bad things about using alcohol. Done.